All right, so now after 4.6, we've now circled back to 4.1. The beginning of chapter 4. So if you remember chapter 3, we talked all about exponential functions. In the last section, I think we talked about graphs of exponential functions. So the end of 4.6, we talked about what makes a function one-to-one, because if it's one-to-one, excuse me, we have an inverse. So, oh, duh, I'm looking at what I need to look at. Okay, so is the exponential function one-to-one? Oh no, my little pen. So if I draw, if we remember our exponential functions kind of look like, oops, either something like that, or they can look like a decay like that, those two things, okay? But if we just talk about our generic exponential, it looks like this. And we see that it does pass the horizontal line test. So yes. Exponential functions are one-to-one because they pass the horizontal line test. You can say thus they have inverses. Beautiful. So the inverse of an exponential function a to the x. So that was like the first kind of when we talked about exponential decay and exponential growth. And then we specifically talked about exponential functions in 3.3 and 3.4. So the inverse to exponential functions are, oh, hold on, my pen. The logarithmic functions, oopsies, LOG, logarithmic functions. And those are, it's f of x, right? And then it's log base a of x, okay? For a not equal to 1, remember, none of our exponential functions, a could be equal 1 either, both greater than 1 growth, smaller than 1 decay, but again, also a had to be greater than 0. So that means that log of a, we would say log base a of b. So instead of saying like f of x, g of x, log a of x, I'm putting log x into this logarithm. It's this other type of function. If you've ever heard of trigonomic functions like sine and cosine, there's a similar concept. So log base a of b equals x if and only if a to the x equals b. Okay, so similar to how inverse worked. Logarithms are a little tricky, but if you think about them like a scorpion tail, it really helps, right? So if I have log of a, I like to do b just so it's kind of b, so it's kind of clear what's happening, but sometimes you don't need, some people don't write those parentheses, equals x. So what that means is a raised to the x equals b. So that's your scorpion tail. So a, oh, there's thunder. Hold on 1 second. Duke's about to freak out. Alrighty, so back, sorry. Oh yeah, so log base a of b equaling x would imply, using that scorpion tail, that a raised to the x equals b. So basically, so you see how this is an exponent, a to the x equals b. So that means that that's an exponent. X is an exponent. So log base a of b is an exponent. It acts like an exponent. It's an exponent. It asks the question, if I have a, what do I raise it to get to b? That's the question it asks. I like to think of these function things as questions. Okay. So where a is the base and the domain is from 0 to infinity. I can't put in a negative value right here because I might not be able to get a negative value always, right? I know log a, we talked about, it can only be greater than 0. So no exponent I'm going to apply to a positive number is going to make that number negative. That is not possible. So that's why I can only plug in positive numbers here. So now we're going to find the following, just kind of getting more practice with logarithms. So log base 2 of 32. So that's saying 2 to the question mark equals 32. Well, 32 is, so 2 squared is 4, 2 to the 4th would be 16. And then times 2 is again with 32. So 2 to the 5 equals 32. 35. Wait, no. 2 to the 5 is 32. So what can I raise 2 to get to 32? I can raise it to 5. So similarly, log base 5 of 25. We all know that 5 squared is 25. So what can I raise 5 to get to 25? I can raise it to 2. It's asking what is that exponent? Okay. So now we have 3. And now I want to figure out what it's raised to get to -9. Well, oops, 2. I know that 9 is 3 squared. So 1 over 9 would be 1 over 3 squared, which is the same as writing 3 to the -2. Remember, the domain is all positive numbers, but the range, we can have negative exponents. We've seen that, that's fractions. So what can I raise 3 to get to -9? I can raise it to -2. Now I have log of 16 to the 4th. Well, I know that 4 squared equals 16, but I'm asking what can I raise 16 to get to 4? So if 4 squared is 16, then 16 to the 1/2, or the square root of 16, will equal 4. This is another thing. Okay. And since the only numbers in here can be positive, I'm not ever going to worry about taking the square root of something that's negative. And same with a also being greater than 0. So we don't have to worry about anything like that. So that's pretty cool. So if 16 to the 1/2 equals 4, log base 16 of 4 is going to be 1/2. Okay. So here I can have whole numbers that are positive. I could have negative numbers, and I can also have fractions. So that's pretty cool. From the definition of logarithms, also the properties of inverses, the reason that we're bringing up this is so I can reverse the function of an exponential function, has these following properties. So log base a of x. This is saying, what can I raise a to get to a to the x? Well, if I have 2, how do I get to 2 to the 5? Well, I raise it to 5. So log base a of a to the x is going to equal x, right? I'm plugging, I'm composing the inverse function and the original function into it. So I should get x back out. This one's a little trickier. A raised to the log a of x. Log a of x, we talked about, that's an exponent. Says, what can I raise a to get to x? And now I'm raising a to that value. So I should get x back out. So these are properties of inverses, which is pretty cool. Okay. This one I think is pretty intuitive. This one's a little bit harder to think about, but you can kind of think about a and log of a kind of like crossing each other out, and then the x falls down into your solution, something like that. Okay. They cancel each other out in the sense of inverse functions and original functions, not in the sense of like canceling out in terms of like we would think of like rational functions of like 5x divided by 5, those canceling out. So the basic properties of logarithms, remembering that logarithms are exponents like we see right here. What do I raise a to get to x? Well, that would be, and I'm raising it to x, to a raised to that question mark exponent, I would get to x again. So log a of 1. What can I raise any random number to get to 1? 0, right? I can raise anything to the 0 power and it's always going to give me 1. 0 to 0 is a little touchy there, but same sense. What do I get to if I, okay, number 2 asks log base a of a, asks what can I raise a to get to a? Just 1, right? What can I raise 2 to get so that I can get 2? Nothing, I would just raise it to the first power, okay? And then the last 2 are properties of the inverses, right? What do I get? Raise a to get to a to the x? Well, I would get to x. And that kind of follows from 2, right? That's like a to the 1. And then if log base a, if I raise a to this something and I get x back out, well, now I'm raising a to that thing, so I would hope to get x back out as well. And again, that's from inverse functions. Okay, so those are basic properties of logarithms. And in 4.2, we expand upon those and we get law of logarithms, which is so fun. I think it's so fun. Okay. Let me kind of jumped ahead in my things. Okay. So now let's do some examples with these properties. So log base a of 1. What do 8 to the question mark equals 1? I can raise anything to the 0 power and that'll give me 1. So 0. Log base 3 to the 3. So like 3 to the question mark equals 3. Well, I know that anything on its own is just raised to the first power. So that would be 1. What can I raise 15 to be to get to 15 squared? Well, I would just square it. So I would raise it to the second power to 2. And then for the last one, what happens if I raise 5 to the exponent such that when I raise 5 to it, I would get to 12? Well, I would get to 12. This one I would just really memorize if it's not as intuitive. That's kind of one of the only things that I suggest memorizing. Okay. Logarithms, the idea of logarithms is a little confusing at first. It took me a very long time to feel comfortable thinking about them. My sister would just be like, always tell me that they're just exponents. They're just exponents. I was like, I don't get it. So if you're not getting it and feeling like you fully grasp it at first, that's okay, because it also took me a very long time, which is why you guys get open book, open note for your exams. So yeah, right. So logarithmic functions and their graphs. So we know that logarithms are invertible because its inverse are exponentials. And exponentials are 1-to-1. So logarithms are going to be 1-to-1. And we know that they're functions. So yeah. Right. I know my domain is 0 to infinity. So I'm not even going to really draw that many things over there. Okay, so now we're asked to graph log base 2 of x. So it might be helpful to draw a little chart, just kind of like what we did for exponentials, right? So these kind of need to be a little bit more thought out though. We can't just do like -2, -1, -3, something like that. Well, we definitely can't do that for x since it can't be negative. So, if I did, this is log base 2 of x. So things that are easy would be like 1/8, 1/4, 1/2, 1, 2, 4, and so on, right? So 1/8 is the same as 2 to the -3. So that would be -3. 1/4 the same as 2 to the -2. So f would be -2. This is -1. Remember, log base anything to the 1 is 0. Log base 2 of 2 is 1. Log base 2 of 4 would be 2. Okay. So 1, 2, 3, 4. 2, 1, 0. And then we're at -1 at 1/2. Like that. So our function is going to look like, and we're increasing on forever, right? It doesn't actually ever plateau. So can log base 2 of 0 be defined, right? We see in our graph that line is going on and on forever. When x is getting really close to 0, 1/8, 1/16, 1/32, f is going to go from like -3, -4, -5. So it's going to keep going and getting more and more negative. But can I raise 2 to any power to get to 0, to equal 0, to actually equal 0? No, it's not possible. I can get really, really close, but I can't reach 0. So there's like what we would say, oh God, my pen's not turning on. Oh no. So we would say that, why is my pen turning on? There is, just like exponential functions have a vertical asymptote at y equals 0. Logarithms have ones at y equals 0. So if you want to think about, they're kind of being like, I remember asymptotes, they get really, really close to, but they never touch. It can get really close to 0, 2 to the -1 million. It's going to be like 0.0000 something. Some numbers though, it's not going to equal 0. It's just going to get really close. So similar to exponential functions, we have an asymptote at x equals 0, which is the vertical line. General graph of f of x log a of x is, let me grab this because I like this graph that I drew. It's a very good graph. And where this is 1, and that would be, this would also be 1, and this would be whatever a is, and that should be f of x log a of x. Okay. Beautiful. And then you can see the horizontal asymptote right there. Okay, so that's what our logarithm functions look like. They're pretty cool. All right, so 4.2, so we're done with this section. So 4.2 is another short section all about logs, and it's pretty fun. So we're gonna learn more properties about logarithms and how to apply them. All right, so I'll see you guys there in a little bit.